my goodness. Wow. Okay, so let's just do a little overview. We started talking about line integrals before the exam. So let's just quickly recap. So remember, there's actually two kinds of line integrals that we're going to do. We've started doing one of them, which is line integrals of a multivariable function, suppose like f of x, y. Those look like this. We're going to integrate that multivariable function over some curve. So the multivariable function is a surface in R3, and that curve is a curve in R2. So it's like we're going to accumulate for all points on the curve at a rate of f, if you think about the rate accumulation version, but we'll talk about that in a sec. So the ds is a little length of c, right? It's a little bit of c. And then so ds dt is the rate of change of length for a change in t. So how much of the curve gets swept out for a change in t? That's what ds dt. And then we use ds dt. We said that was the same as what the absolute or the speed function or the magnitude of the r prime function, which defines c, right? The r function defines c. ds dt would then be the magnitude of r prime, and we use that to substitute in for ds. So ds is going to be the magnitude of r prime dt. And then we're going to write the function in terms of t, and so then we have a single integral in terms of a single variable. And we can solve that. And we set up an easy one last time for like a parabola. So like I said, the rate or accumulation interpretation of this would be like the net accumulation for some quantity for ordered pairs along C if the rate of change was a multivariable rate of change function f. Okay, that's not as common. More common is a geometric interpretation, and so it's kind of like the area of the curtain, or the net area of the curtain, determined by C. C is the profile, and then the height of the curtain at different levels would be the f, right? So that's the more common. So let's look at an example of that. Let's do another example. That text isn't great. Can you read that in the back? Barely. It says the height of the roof of a building is modeled by fxy equals 10 minus 1/8 x squared minus 1/12 y squared. So this is some architecturally interesting building, right? Like maybe like a convention center or something, you know, like a display, some, you know, public art or something. And then, so the wall is the gray, and that's that wall from the floor to the roof is along 2x plus y equals 8. So the gold is like this like roof wall thing, and then there's a wall, a vertical wall at 2x plus y equals 8 in the first quadrant, and so we want to find the area of that wall up to the roof. So can you see what that's asking there? So it's asking for so can we find the area of that right there? And this is a perfect application of our line integral, right? Because that's exactly what the line integral finds. As long as that function is always positive, it's going to find the area down to the xy plane. Okay, so can we do it? So our line integral is integral C we know we're going to have to write that all in terms of t. And to do that, that means what is c here in this case? So looking at this example, what is c? Yes, sir. Okay, right. So c would be the 2x plus y equals 8 in the first quadrant. That thing right there is our c. And so we need to write c. So it's in order to write the single integral in the single variable t, it's all based on the parameterization of c, right? The parameterization of c as a vector function, right? We did that back in the day. So can you write that segment c as a vector function? Meaning x is some function of t and y is some function of t that gets us all the points along that segment. Can you do it? Anybody? What's that?
I would just solve for with your equation. I would just solve for y. So
Yep.
y equals 8
Yep.
minus 2x.
Uh-huh.
You can just make t equal to x.
Right?
And y would be 8 minus 2.
This is a real common technique. If you don't have a circle or an elliptical function that you're parameterizing, make one of the variables equal to t, and then figure out what the other will be in terms of t. So then y would be
8 minus 2t.
8 minus 2t. Okay, and so from there, we're going to rewrite the function in terms of t, and then you're going to find the magnitude of, so this is our ds, right? That's our ds. A little bit of arc length would be like the rate of change of the curve times a little bit of t would give you a little bit of arc length. So can you do it? So can you rewrite f? Here's f. You're going to rewrite that in terms of t, and then you're going to find the magnitude of the derivative of our r function, dt, and then you got to figure out what your limits of integration are, t1 and t2, so that you traverse that specific segment across the first quadrant. Think you can do it if you had help with the person next to you? Can you finish this example? So yeah, so either you're making progress or you're getting help.
The x values are not 0, x t is 0.
Okay, how about Andrew back there? You were able to rewrite the function in terms of t? Were you able to rewrite the function in terms of t?
Yeah.
Tell me about that. Tell me what it is.
So 10 minus 1 squared minus 112 is 8 minus 2t squared.
Yeah, so why can we do that? Because we only care about the function over c. And over c, x equals t and y equals 8 minus 2t. So if we only care about the function over c, then we can just make x equal to t and y equal to 8 minus 2t. And we got our function. Okay, very good. And then what about the derivative, or the magnitude of the derivative? Alyssa, did you get that? What's that? Oh, is that what you got too? That's okay, no problem. You got square root of 5. How'd you get that?
We took the derivative of RT
Uh-huh.
and we got 1 and -2 and then
Right. So there's our derivative. That might be a function of t. In this case, it's just a constant, but that could be a function of t as well, right? If you didn't just get 1 and -2 and you got functions of t, then that magnitude of r prime could be a function. All right, and then last question is, what does t vary from?
0 to 4.
So y is 0 to 4. You want to?
So it says that x is greater than 0 and y is greater than 0.
Okay.
So for the x greater than 0, you know that t has to be at least 0 because t is equal to 0 to x value.
Okay, x and t are the same, right? So we're going to do x equals 0. That's x equals 0 there. Okay.
And you also know that y has to be greater than 0. So I just said that the 8 minus 2t is greater than 0. And I solve for t there, and t has to be less than 4.
Okay, yeah, so we need the x coordinate right there. Right? And that's just 4. So what you said was fine. Or you could think of it as we just need the x coordinate there. Yeah. So we're going to go from. Now we have to be careful with that. What is the direction of the curve? Remember, there's direction to the curve. Is that? We go from 0 to 4, we're going this way. So there's a question of if we went from, which way do we go to make it positive? Because we go from 0 to 4 and then we go from 4 to 0, one of those is going to be positive, one's going to be negative. So we would want, however it's going to make this thing positive. We know that this line integral is going to be positive because fxy is always positive. Has anyone solved this?
Yep.
Is that,
I got a 272 square root 5 all over 9.
and that's when you go from 0 to 4?
Yeah.
Okay. So what was it again?
272 square root 5 all over 9.
Over 9?
9, yeah.
And let's just get an approximation for that. So it's because, right, if you were building this thing, this is not how you would talk, the engineers would talk to each other. You wouldn't say that. So what would be approximation for the area?
That was 67.57.
And that would be units squared. So whatever our axis units are in, those square units would be how much area this thing is, if that's right. Okay, any questions on this example? So that's the first kind of line integrals, and there's another kind of line integral, and those are, rather than line integrals of real valued multivariable function, we can do a line integral of a vector valued multivariable function. And what is a vector valued multivariable function again? What do you get when you have a vector valued multivariable function? Remember what that is? What's that? That's a vector field, right? That's a vector field. So we can do line integrals of vector fields. Let's take a look at that. Okay, so here's some vector field, okay? And then I have a path through the vector field. So the vector field would be so Rxy would be what, some two functions of y, like right? Multivariable is referring to a location in the plane. That's our independent variable. There's actually two variables, x and y. And then the dependent thing is given a location, there's a vector associated with every location. That's what we know as a vector field. So the easiest way to think about line integrals through vector fields, it doesn't have to be this, is if this was a force field. So if this blue vector field was a force field, so we're in a force field, say F. like what I just wrote here. Okay, and then this is some path through the vector field. Some path C through the vector field. And so think about maybe this is a wind field, okay? Maybe so this is at every location. There's some magnitude and direction of wind at every location. And this is like the road, and we're on a car, and we're going to drive the road through this wind field, okay? And so then what happens is, as we drive, the wind field will help or hinder the effort of the car, right? Okay, and so if we say, so maybe right here at this point is a vector like that. I'm trying to just look at the vectors around, and no, maybe not. Maybe more like this. All right, so suppose that's the vector associated with that point, okay, on the curve. And so what part of that force, and then if we have like a little ds, or a little dr vector, so C is defined by some vector function of t, and so got a little vector right there that's so for some point there's dr, right? A little bit of the curve, dr, and then I have at that point I have my force field vector at that point. So this is dr at x naught, y naught, and this is f at some say step 1, x1, y1. And so what's going to help the car? The parallel component, like as much as they're in the same direction or as much as they're orthogonal? Parallel, right? So what do we want to accumulate? We want to accumulate f we want to accumulate those wind forces in as much as they're in the same direction as the curve or orthogonal to the curve? Same. Therefore, we want dot product, right? We learned that. And what are we actually accumulating here? F dot dr. What was that? Remember? F force times a little bit of distance. This is work. Remember our work was dot product, right? Work was force dot dr. So this is gonna be a little bit of work. Dot product will live as scalar, right? So we have that, are taking the product of the magnitudes of f and a little change in as much as they're in the same direction is gonna give us the part of this force that's helping the car, right, along the direction of dr. And that'll be a scalar because dot product gives a scalar. And so that'll be a little bit of work at that moment along the drive. So what we want to do, so the total work then would be the integral, the accumulation of all those little bits of work as t goes from, or over c. Over c. This should make sense. So if we're going in the direction I showed, so if here's our starting point and here's our ending point, do you think the work is going to be positive or 0 or negative? So the work that we're calculating is not the work the car does, but it's the work the force field does to help the car. That's what this calculates. It's the integral of f, right? So if it's the integral of f, then it's the work that the force field does whatever it's doing to aid the car along the path. So is that going to be positive or negative? This is going to be positive because look, so all along here, the component in the direction of the curve, the components of the forces are in the direction of the curve. What about through here? So we got, yeah, there's like a section here that's like orthogonal. So what would the net work be through there? Around 0. And then when we turn the corner, we get a little more help, right? So clearly, this is a positive amount of work that the vector field is doing. So if the vector field is pushing against the car and making the car do more work, then that's a negative work. That's the vector field doing negative work on the car. It's making the car exert more effort to do its path. But if the vector field is helping the car, aiding it, that's positive work. And there'll be a net, there'll be a net effect throughout the path. In this case, most of the way it's positive. There's a little bit where it might be 0. Clearly, this line integral would be positive. So again, just like with the other vector line integrals, we need to parameterize C in terms like as RT. Okay, and then dr, so then r prime of t is just the derivatives of the x and y components. And that's dr dt. So the dr will just be those derivatives dt. So that's what we'll use. That's our dr. And then you'll have the dot product of that with the force field written in terms of t, right? So again, change it from xy to t. It's an arrow. It's supposed to be an arrow. And then it'll be the starting t to the ending t, right? So we're going to rewrite the force field in terms of t according to r, according to the path r. Our dr is going to be the derivative function times dt, and then we'll have the starting t and the ending t. So we'll do an example of that in a sec here. But let's take a look at another one. We'll just see if we think it's positive or negative. All right, any questions on the setup here? So this is the easiest application to kind of understand line integrals of vector fields, but it doesn't have to be work, okay? So this field could just be any field and a path through any field. And so then the line integral will just be like the accumulation of all the components of the vectors in the direction of the path. But kind of the easiest way to understand them is really as the total work through a force field. But this doesn't have to be work. It doesn't have to be a force field, and then you wouldn't get work. You'd get some kind of accumulation of the components of the vectors across the path. Anybody have a question? All right, just another practice. I thought I had another one here. Let's see. This one. So I want to go clockwise. I want to start here and go this way. And I just want you to, as just a quick exercise, predict whether you think that integral will be positive or negative. All right, so I'm going to start here. I'm going to end here. So T0, T initial, T final. So I want you to inspect this a little bit and see, what do you think? Would this be, do you think this line integral will be positive or negative or close to zero? So think about that. Okay, what do you think? This one might be slightly subjective, but maybe we can come to consensus. What do you think?
Negative.
He said negative. Agree with that? Some people are nodding. Yeah.
Close to zero.
Negative and close to zero. Not, yeah. So why? So tell me, how are you coming to that conclusion?
Because the top left part is positive.
Positive through here.
The C is very slightly negative because of the part next to the X.
The whole thing is C.
Oh, well,
Yeah, the whole-
top
yeah.
right quadrant.
Yeah. Okay.
And then the bottom right part is more negative and the top left part is positive.
Okay. Right. So we got some positive, a little bit of zero, and some negative. And then how do you arrive at the conclusion of negative?
Because the part in the bottom right quadrant is longer than the part on the top left.
It looks like we spend more of the path going against the vectors than toward. Okay? So now if these vectors here were like this, say those vectors over there had greater magnitude.
Would it be positive or close to zero?
Yeah, so maybe now closer to zero or even positive. So there's two things going on. How much of the path is against or for? You know, how much of the path is the vectors are pushing or pushing against or pushing from behind? But then the magnitude of those vectors are play into it as well, right? So it's both little bits of the distance, but then also the magnitude of the vectors both play into it. So if that positive part, even though shorter, the magnitudes were bigger, then it would win, okay, in the overall accumulation of the vector components. Okay, so let's do an example here. And it's on another screen. This one. Where are you? Okay, so I'm going to find the line integral of this vector field, xy and 1 minus x. Given that C is the part of the circle with radius 2, centered at the origin from 2, 0 to negative 2, 0. So let's graph. I have not graphed the curve, but I'll show you the vector field. Okay, and now I want to draw this path. So what should I type in to draw this path? And I want that to be in terms of a vector function. So I want you to figure out, and this is going to be part of the problem, you're going to have to write the vector function for C, parameterize C, and then find the line integral of the field of that field over C, going from 2, 0 to negative 2, 0. So let's just predict. Do we think that that's going to be negative or positive result when we do that? Saying negative. Is it negative, maybe 0, or definitely negative? Definitely negative, right? Because through here, negative, although small, definitely negative. And then maybe somewhere 0 through here, and 0, kind of 0-ish, right? 0-ish. But in the end, a little bit more negative again. See that? So there's really no positive contribution along the way. Negative, 0-ish, negative. So we expect that this line integral will be negative. Okay, I'm going to take attendance. This is for you to work on. So we have to do parameterize the curve and then set up the line integral in terms of t, and we're expecting a negative result. Okay, so I need to express this function, express the curve. How do I express the curve? Yanni, did you get that? Give it a shot.
So I need to express it in terms of
Yeah, so this is parameterizing a curve, right? So we're writing a vector function, parameterizing the curve.
I just got like a very first part. I know it's like a circle, so I just got x squared plus y squared equals 4.
Okay.
I don't know how to make the line.
So that's the equation of the circle, but then when we have circles, how do we parameterize them, right? How do we write a vector function for a circle instead of an equation of the circle? Remember? Yeah, that'll work, but it's not the natural way to do it. It's not the natural way to do it. So what is the natural way to do that? Yeah. So Ada, what is it? That'll work, but it won't be. So you could do this, but then you're going to have to get it to go from 2, 0 to negative 2, 0. You're going to have to do more thinking about what t would be. So
Flip sine and cosine.
yeah. So if we flip sine and cosine, then that makes getting the starting t and the ending t really much easier. Does that make sense? Yeah. So that sine t and cosine t will work, but then you're going to have to do a little math to figure out what t is going to start me here and get me going counterclockwise around to there. All right. But this, then t will just go from what to what? 0 to pi, and that's enough to think about it. So let me get that in there. So there we go. So this is what we're doing. Okay. Did we make more progress than that? John, you had your hand up. Did you make some more progress than that? So what are we trying to do? We're trying to calculate integral over c of what? Of? What are we calculating? So what's the general form of what we're doing?
Oh, it would be f of x, y, and ds.
Nope, that's the line integral of a multivariable
Oh.
function.
F
What-
dot dr.
F dot dr, right? F dot dr. So we want to write this whole thing in terms of t. That's the point. We're going to single integral to solve it. We need everything in terms of t. So that means we need to get f in terms of t. So what will that be? Someone was saying it? Go ahead. All right, I'm going to use c and s for cosine and sine, okay? So c means cosine, s means sine, okay? Dot dr. Yeah.
That'd be negative 2 sine t, 2 cosine t.
He wants negative 2 sine t, 2 cosine t. Agree with that? Yeah, so it's dr, that's dr dt, and then if we want dr, then we multiply by dt. We get just dr. So it's going to be negative 2 sine t and 2 cosine t. Am I going to make it? dt. Got it. Oh, no, it's not. Okay. And then t is going to go from what to what? 0 to pi because we used cosine and sine for x and y. All right, so that's the setup. Did anyone get it before I started? Anyone have it before I started? One? Most of it? Okay, so, all right, so does that make sense? So it's not, this isn't really too hard. You get x, y, so your vector function is x, y, and 1 minus x. Parameterize the curve, so that's what we're going to use for x and y to rewrite f. And then we need the derivative, dr, it's dx dt, dy dt. And now we're going to evaluate the dot product, and we'll have a single variable in terms of t. Does it make sense? So what will that be? Negative 8 cosine sine squared. Is that right? Plus 2 cosine t times 1 minus 2 cosine t. And that whole thing dt. Did I do the math right? Dot product from 0 to pi. So now we're going to remember our trig integrals from Calc 2, right? Trig integrals? Question? Or
No.
Are we good? So this one, this is like a chain rule, the results of a chain rule. So it's like negative 8 times, what, 1/3 sine cubed? Does the derivative of that give us that one? This should be a 3. What's that?
Should the number be positive?
No, because the derivative of sine is positive cosine, right?
Okay,
Yeah, so I'm gonna do power rule on the sine. I've got the cosine for the chain rule in there. So that antiderivative is 1/3 sine cubed t minus 8. And then I got plus 2 cosine t, so that antiderivative is just 2 sine t. And then I got minus 4 cosine squared. Remember how to do cosine squared t, antiderivative? Anybody remember? Nope. It's the half angle formula.
Oh,
Cosine squared t is 1/2 1 plus cosine 2t. Remember that? It was just this one thing you had to memorize, to be on the lookout for. If you just have plain cosine squared or plain sine squared, you do the half angle formula. So it would be negative 4, half angle formula gives 1/2 1 plus cosine 2t. So we're going to do the antiderivative of that, which is, that's negative 2, so we'll have minus 2t, it looks like. And then minus 2 cosine 2t. Antiderivative is minus sine 2t. And it turned out easier than I thought. If we're not sure, take the derivative. Derivative of that would be negative cosine 2t times 2. Negative cosine, yep, that's it. So I think I have the antiderivative. And then we're going to evaluate from 0 to pi. Hopefully we get lots of zeros here. So at pi. So at pi, this is, that's 0, that's 0. We'll get negative 2 pi, and that's 0. So at pi, this whole thing is just the negative 2 pi. At 0, 0, 0, 0, 0. Answer? Negative 2 pi. What we expected? Right, because negative, we expected negative line integral because we're going against the vectors most of the way.